Welcome to Dr. Jed's continuing calculus video series. Today's lesson is section 5.5 from Rogowski, net change, which is just an application of the fundamental theorem of calculus again. We've had 3 sections of the fundamental theorem. It's that fundamental that it's worth actually studying this much. First we'll talk about the rule and how we're looking at it slightly different this time. We'll do some examples. Hopefully we'll be done early. Let's see. What is the fundamental theorem, at least from our standpoint now? The integral, I'm going to count it with t's now, from t1 up to t2 of the derivative of s of t dt. There's a couple changes here, but that function, the integral, is its antiderivative at the top endpoint minus its antiderivative at the bottom endpoint. How is this different? Well, it is the fundamental theorem. That's all there is to it. Except we're talking about it slightly different. Couple of things. First of all, t isn't for time, but that's not really that important. What's really important, the only thing that's really, well, there's an s, but the really important thing is this is a rate of change. This is a derivative. Now, it was a derivative before, when that was a little f, and those were capital F's. It was the derivative of that. But this was the function of interest. Now, that's the function of interest. Typically, we use s for position, where s prime might be like velocity. So this is saying the integral of, or rate of change, the integral of velocity, is the change in position. So if you start here, and then you move 8 inches this way, in the positive direction, this is not what the integral is. The integral is the difference in these two, so it's 8 inches. If you start here and move 3 inches in the negative direction, the integral is this difference, so it's -3. So we're talking not about finding s, we're talking about finding how far s changed in this amount of time. This rate of change, so it can work with s is for position, it can work for marginal cost, it can work for the rate of flow, the speed of, electrons in an orbital would probably be another velocity question. You could talk about anything where you have a rate of change here and you want to know about something about the original function. So let's do an example. As you might guess, S also stands for story. These are a lot of story problems. The marginal cost to produce X buckets of tuna-flavored ice cream. Probably not going to be a bestseller, but let's go with it. Anyway, the marginal cost, we've studied marginal costs. They're the derivative of C. Actually, it probably really would be, it'd be popular with cats. Anyway, here is the marginal cost. So we're starting with the derivative, and we want to know something about the original cost. What do we want to know? We want to know how much more does it cost to produce 100 buckets than it did to produce 50. Okay, so we're going to use the theorem here. We want to know another thing too. How much total does it cost to produce 100 buckets? Probably not going to be producing many more than that. But let's not worry about that issue. So these are 2 different good questions. How much more from 50 up to 100, and how much total for 100? Not enough space to do it here, so let's move over to the next board and answer. I've rewritten the marginal cost, and I've partially answered the original, actually I fully answered the first question. To go from 50 to 100 is the net change. The net change from 50 to 100. So we integrate from 50 to 100 of C prime to get the change from C100 down to C50. We don't know this C function, so we have to anti-differentiate. And if you look at this, the antiderivative of this is just here. What did I do? Have that to make that squared, put the x here, and there's a number at the end. What is that number? That's the plus C. Because you could put any number you want there, take its derivative, and that number, poof, disappears, right? Any number you want can go there. Doesn't matter which one you pick, because look what happens. When I evaluate at 100, when I evaluate at 50 and take the difference, that number minus that number, it will go away. I've done all of the algebra stuff here, and that's the change in cost. Those extra 50 buckets will cost you $1,585. That's the first question. What about the total for 100? Because that's a good question, not just how much more does it cost, but what's the total? And you might figure, well, the total is going to be the integral from 0 to 100. of c prime of x dx. But that's not really what we want, because what is that going to be? The net change says it's c of 100 minus c of 0. That's not the total cost. That c of 100 is the total cost. What's this c of 0? Is that 0? Well, it's the cost to produce no ice cream. You know, that sounds like it should be 0. But if you ever run a business, you'll know, before you produce your first good, before you produce the first car, the first set of ice cream, the first whatever, you have initial costs. Those initial costs are in here. The cost to produce nothing is your initial costs. So this will give us 100 buckets worth, but it won't give us that initial cost. What we really want is this. That's the total cost. And we actually found that already. It's equal to, from over here, I'm standing in front of it, but 2170 plus some number. It'll cost us $2,170 plus some other extra amount, which is the initial cost. But we don't know what that is. There is no way, from the derivative, from up here, there's no way to construct what that number actually is. That's a mystery. That's something we can't solve. The net change talks about how much more it costs than here. So from here to there. Doesn't talk about the total. Can't talk about the total. This is one of the drawbacks of this analysis. We can't know what that is. So let's talk about another case. Let's talk about velocity. We can talk about velocity. We can't know where the position is, but we can talk about the change in position. So our velocity function, v of t, is going to be 6.3t minus 4.2 meters per second, say. Now, what do we do with that? There's two questions I can ask. I can ask, find the net displacement and the total distance traveled. Those are not the same thing. If I start here and I move that way, 100 centimeters, and then I move back, my displacement is 0. But the total distance I moved is 100 plus 100. It's 200. So these are different questions. Displacement is going to be just this net change theorem. That's going to be great. We can use that. Unfortunately, distance traveled doesn't do that because, well, integrals, we've spent some time studying integrals. Integrals are signed area. There's positive parts, there's negative parts, and we add them together and they cancel out. But if we want to talk about total distance traveled, the positive and negatives should not cancel out because going that way and then coming back still puts that many miles on your car, regardless of if you ended up in the same place. So how do we fix that? There's an easy way to fix that. If you're actually interested in the total amount of movement in your car or whatever, we can simply turn this always positive. We put an absolute value on there. So what do we do here? Well, this first one is actually easy. This is going to be the antiderivative of that. So 6.3 over 2 t squared minus 4.2t, evaluated at our two spots, t equals 0 and t equals 1 second. Plug 1 in, we get 3.15 times 1 squared minus 4.2 times 1. Plug 0 in, you get 0. And I get a negative 1.05. What are the units going to be? Well, dt right here, seconds, velocity, meters per second. Meters per second times seconds is meters. The dt actually has a use. In units, it means something. So that's the answer to the displacement. What about distance traveled? Absolute values are very, very hard to integrate because, well, they've got that angle. You can't anti-differentiate because there's no way to break that. But you can break it apart. You can break it into the positive part and the negative part. So all we need to do is figure out where the velocity is positive, where it's negative, do both pieces separately, and then we're good. So here's our velocity function. Where is that positive? Where is it negative? A better question? directly answering that is, where's that 0? So where is that 0? Bring things over, divide out, you're going to get t is 2/3. That's where it's 0. So what do we have? Well, beforehand, put a 0 in here, you've got negatives. Afterwards, you've got positives. So how do we rewrite this for negatives and positives? Before the 2/3, from 0 to 2/3, we have negatives. How do you make an absolute value of a negative? Well, you remove the negative sign, but if you can't just remove it, you can attach another one. After the 2/3, it's positive. So we really don't need to do anything. Well, the antiderivative is going to be the same, except it's going to have minus signs involved. What do we have? We have this one's the same, except it's got minuses. So minus 3.15t squared plus 4.2t, evaluate from 0 to 2/3, plus 3.15t squared minus 4.2t, evaluate from 2/3 to 1. That's going to be messy. The 0 will make that all 0. The 1 will make that actually what we had before, but now we have that 2/3 piece. So what are we going to, we're running out of chalk space, so we kind of have to figure out what to do here. But I plug the 2/3 in, got minus 3.15 times 2/3 squared plus 4.2 times 2/3. Well, a third of that's 1.4, so that's going to be 2.8. That's what we get from this first one. What do we get here? We get, plug the 1 in, you get negative 1.05. That sounds strange, because we're talking about positives now. But that's okay, because the other one is going to be all of this. So minus, plug all that in. So minus 3.15 2/3 squared. Minus makes plus the 2.8. See, that's where the pluses and minuses start to cancel out. This is going to be a messy calculation. Well, a third of this is 1.05. We could probably do the calculation. But you know what? It's numbers. So let's simplify it a little bit. I've got a 2.8. I've got another 2.8 is 5.6. I've got a 5.6 minus 1.05. Get rid of the units. I've got 2 of these. So I'm going to have plus 8/9 of minus 3.15. 8/9 of that. 24 plus 8. 25.2 divided by 9. Well, it's a number. And it's not going to enlighten us to do it. You can see the top one, pretty easy to do. The bottom one, it's not a conceptually weird thing, but it's messy. These will always be messy. These ones will be less so. Maybe it took longer than I thought, but that's it. Hopefully it made sense, and we'll talk to you later.